Okay. And share screen. All right. Let's start our time with prayer. Dear Heavenly Father, thank you for another session, for another week, and another session that we can study mathematics and see your wisdom and also a glimpse of the beauty of your work in the universe. Lord, we commit our time into your hand. May you guide and lead us, and I ask your blessing upon all these dear students, both in the class and online. Bless them in this course, help them not to be afraid of math, help them to do excellent, and may they be able to use the skills that they learn, the knowledge that they gain in mathematics in the ministry for your glory. And bless them with their different ministries, bless their families, keep them in good health. We commit our time into your hand. In Jesus' mighty name we pray. Amen. Okay. Before we go to the lesson, let me just remind you. So this week you are going to do assignment number 3, and then do a summary report for chapter 3 of Nichols, and take quiz 1. So 3 things: quiz 1, assignment 3, and the chapter 3 reading report from Nichols. Submit them please by Sunday before midnight, and also please choose a chapter from Nichols as soon as you can for your PowerPoint presentation at the end of the course. Any question? Do you guys have any question? No. All right, then let's go to our lesson. All right, wanted to, last week I mentioned about the Heisenberg uncertainty principle that shows the limitation of human knowledge. Heisenberg was a German physicist back in the 1920s, so almost 100 years ago. And he came up with this equation, which delta x times delta rho, right, that's not a p, it's rho, means change in momentum, or simpler way, energy, always greater than or equal to Planck constant or Planck bar, when you have that dash, over 2. So, and just let me show you what this component means. And don't worry, this is not going to be in the test or anything, just for your knowledge. The Planck constant is a relationship between energy and the speed of light and wavelength. These are constant, and the h bar is a reduced Planck constant. It's divided by 2 times pi number. And basically, Planck constant is a constant that, in quantum mechanics tells us energy is exchanged in a specific amount known as quanta, and Planck constant defines how much energy in these is in those quanta. Now coming back to the formula, you see that's a constant, and that's number 2, numerical value, digit 2. It says a change in a position times a change in momentum or energy, it's always greater than or equal to Planck bar h bar over 2. In other words, if we want to increase our precision or accuracy of a position of something, of a electron, atom, or as I mentioned, like let's say take my cell phone, for example. If you want to increase more precisely where it is located, if I keep moving it, it will cost you. The cost would be the momentum, or your knowledge of the momentum has to go down. The change in a position, the more precise you want to make it to be, has to be the product of that times the product of the change in momentum should always be greater than equal to Planck constant over 2. So if you increase 1, let's say if you, I don't know, you can't see my arrow, can you? No. If you increase, if this goes up, or if this goes down, meaning the precision, you're getting more precise reading on about the position of a particle, this must go up so that this equality or inequality will hold. So there is always, if this goes down, this must go up. So there's a limit to human knowledge. And the interesting thing about this equation is it's based on constant. I put it in the PowerPoint, so I updated it. So it's based upon constant. So it doesn't matter how much human technology knowledge changes. So 500 years from now, still this equation holds, and it shows there's a limit to our knowledge. We need information from outside the box. We need revelation to tell us about our environment and how to live in that environment. All right. Okay. So today we are going to talk about sets, and that's very important because it helps you. The whole mathematics, the whole algebra, it's based upon set. You know, we can have a set of dinosaurs, set of cars, vehicles, butterflies. You can have set of zoo animals, a group of things that they have some things in common and some things not in common. That forms a set. So when we talk about set, a set is a collection of objects which are called the elements or member of that set. So, like in the previous diagram, we had, you have like the set number 1, set of dinosaurs. Those are the member of set 1. Then a set is well defined if its content can be clearly determined. When you clearly know what are the members of a set, that means that's a well-defined set. For example, a set of undergraduate student at Southern California Seminary is a well-defined set. But a set of how can I say this? Let me take up an example. A set of let's say old age student is not a well-defined set because it depends on your definition of what is old or what is young. See, because that's not well-defined, that cannot be a well-defined set. Now, we have 3 methods to identify a set or indicate a set. Number 1 is we describe it. A set of dinosaurs, a set of cars. Number 2, we use roster form. And number 3, we use set builder. Basically, some of these things you guys have to memorize. As I mentioned, mathematics is like any language that it has its own vocabulary and grammar. And some things, like any language, when you study Greek, Hebrew, you got to memorize. You have number of memorization. We have some of that in math, but again, as I mentioned, provided that you understand the principle, the amount of memorization is not much. So the first way to describe a set is just giving it a description. So, for example, we can talk about, somebody write a description of the set containing elements of Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and Sunday. Well, the description of that set, these are the days of the week. So this set would be the set is the days of the week. That's a description. Now, if we want to put it in a roster form, we put the elements, we write them in a braces, a pair of braces, and we put comma in between. For example, if I have, as you can see here, braces, and then inside of it, it's 1, 2, 3. It's a roster form. This is roster form notation for the set whose elements are 1, 2, and 3. But if you put parentheses, that's not roster form. Parentheses do not indicate a set. Okay. And then a set is generally named with a capital letter. For example, if we have a set of natural numbers, we call it, usually it is called by capital N. Okay. All right. So this is a set of natural number. You have N is equal, N as a symbol, equal to, then you have the braces, and then you have natural number 1, 2, 3, 4, 5, comma, and then you have those 3 ellipses indicating that the element in this set continues in the same manner. All right. Now, how about the roster form? For example, maybe they ask us to express the following in the roster form. We want to express the set A. You see, this is a description. Set A is a set of natural number less than 5. So the answer, the natural number less than 5 are 1, 2, 3, and 4. So if we want to put that in a roster form, it's going to be A as a name of the set is equal to, then braces, and you have 1, 2, 3, and 4 with comma in between, and then you close with another brace. Now, number B is a set. B is a set of natural number less than or equal to 75. Okay, so I write B equal, then you open braces, and 1, 2, 3, 4, and you don't need to go all the way, write all the numbers to 75. You write 1, 2, 3, 4, comma, and then put 3 ellipses, and then comma, and the last number 75. Okay, so, and notice it says it's a set of natural number less than or equal. That's why you write number 75 there. If it was saying less than 75, you wouldn't have number 75. You go all the way up to 74. Or set P is a set of planets in Earth's solar system, then you P equal to braces Mercury, Venus, Earth, and all the way to Neptune. And some people add Plato or not. Okay. Now, a set can be inclusive or a set can be not inclusive. The set of natural number, for example, if it tells you write a set of natural number between 4 and 9, it means do not include 4 and 9. So it would be 5, 6, 7, and 8. A is equal, brace 5, 6, 7, and 8, close the braces. Now, if we want it to become inclusive, would be different. For example, if I have a set B, braces 4, 5, 6, 7, 8, and 9. Here, the word include, it says inclusive, a set of inclusive, a natural number between 4 and 9, inclusive, meaning include 4 and 9. Okay. That clear? All right. Now, then we have set builder notation. A set builder notation here. or a set generator notation may be used to symbolize a set and is frequently used in algebra. When you have that symbol, look like an E, it means it's an element of, is used to indicate a membership in a set. For example, if I have a set A, which are its members are 5, 6, 7, and 8, then I can write 6. Then you put that sign like an E sign. So E6 is a member of A, or 6 is a member. Put the braces 5, 6, 7, and 8, 10, because 6 is right there. But if, for example, if you choose number 9, no, 9 is not a member. So you have E and you have a dash going over it. All right. So the set builder notation, if in a quiz, in a test, homework asks you to write in a set builder notation, that's it. So you put a pair of braces, then you say X, all of X, then you put a vertical bar. That means such that X is less than or equal to 2. This is just for example. So it's asked you to write a set. Now, it hasn't told you what X is. That depends on what X is. But it's asking for a set of whatever which is less than or equal to 2. Here we have, okay, here. I hope you can see that. For example, the first one, it says X is less than A. You know, that's a sign for being less than. X is less than A. In a set builder notation would be, you put 2 braces, X such that the vertical bar, X is a part of a natural number, but is less than, no, A is defined for us here as 4. So that's a set builder notation, okay? If I wanted to write it as a roster notation, it would be all the natural number less than 4, which would be 1, 2, and 3, all right? The second one, X is less than or equal to A, okay? Yeah, that's basically the meaning of the inequality. In a set builder notation, again, the braces, X, such that X is a member of natural number and is less than or equal to 4. Now here, because it says less than and equal, you have number 4 also. All right, let's do, for example, let's do this one. X greater than A and less than B. Okay, so in a set builder notation, you write, again, 2 braces, X, vertical bar, X is a member of natural number and is greater than 4 and less than 8. So it has to be 5, 6, and 7. Here, X greater than and or equal and less than or equal to B. Same as before, except that now we made it inclusive. So you have to include 4 and 8. Yeah. So remember, this is a set builder notation. This is a roster for, and this is basically the description. If we go here, X greater than equal to A but less than B. Again, X is a member of natural number, so greater than equal to 4 but less than B, which is 8. So you have 4, 5, 6, 7, or vice versa if you reverse it. If you say X is greater than A and less than or equal to B, you include 8 and you exclude 4. Okay. Now, another thing to remember is a cardinal number. These are, again, mathematical vocabulary. The cardinal number of a set A is the number of distinct elements in that set and is represented by n of A. Let's see. This is simple, but if you want, we can go to page 50. Example 8. Set A is in the middle of page 50. Example 8. Set A is natural number 7, 9, 11, and 13. What would be its cardinal number? If I have a set, its members are 7, 9, 11, and 13. What's the cardinal number? How many members are in that set? How many elements? 4. That's it. Set, let's go to set B. Set B is a set that contains 0. What is its cardinal number? 1. Yeah, 0 is a number. It's 1. Set D, you see that symbol with it looks like a circle with a dash going across it. It means null, empty set. Now, what's the cardinal number for that one? 0. Null means nothing. Empty. It's an empty set.
But empty is nothing then, right?
Yeah.
All right.
Yeah. Okay. So remember, if it's a set that has 0, only 0, it's not empty. It has a member. Or if it was 0 and 1 and 2. If it was 0, 1, and 2, what would be the cardinal number?
Sorry?
If it would be if I have a set that its member are 0, 1, and 2.
3?
3, yeah.
Okay.
Yeah. But null, which is that circle with a dash going across it, means empty. All right. Now we have finite and infinite set. A set A is a finite set if the cardinal number is either 0 or a natural number. Either like all the examples that we looked at, those are all finite set. It's either 0, like a null set, or it has some natural number, like 4, 1, 3. Okay. Now, a set whose cardinal number or cardinality is not 0 or a natural number, it's an infinite set. Let's see. For example, a set of natural number is an infinite set because it goes on and on and on. All right. So, and we also have something which is called a universal set. That's all the elements, members of any group that you're looking at or you're considering. A universal set for students at Southern California Seminary would be all the students. Male, female, graduate, undergraduate, full-time, part-time, everybody. All right. And the cardinal number, the universal set, its cardinal number is infinite and is assigned as aleph, null, aleph from Hebrew alphabet, and that little looks like a O or 0, it means null. Okay. The cardinal number of an infinite set. Okay. All right. Now, we talk about equality of sets and inequality of sets. Set A is equal to set B means that set A and set B contain exactly the same member, same element. regardless of the order of their position or repetition. And when two sets are equal, we write them A is equal to B. For example, if set A, and notice again, I put the braces, has these letters, W, X, Y, and Z. And then I have set B has Z, Y, W, and X. We can say A and B are equal because they have exactly the same elements. Even if I had, let's say set B had Z, Y, W, X, and again another Z, there was a repetition, still they are the same because the members are the same. Okay. Let's look at example 10 on page 53. For example, we have example 10, page 53, number 8. We have a set 4, 8, 9, and the other set is 8, 9, 4. Are they equal or not?
Yeah.
Yes. If we have a set, number B, 1, 3, 5, is it correct? Is it true to say it's equal to the other set? No. Why?
Because there's a 0 there.
Yeah, the other set has 0. Okay, I guess that's, look at the, that the bottom is a checkpoint number 10. You have a set OLD and a set DOL. Are they equal? Yes. Number B, you have a set 4 and 5, and you have a set 5, 4, and null. Are they equal? Yeah, null is nothing. Nothing is nothing. Good. Now, we have subsets. We have subset and proper subset. Set A is a subset of B when it's symbolized by A. You have that kind of a fallen U. A, and then there's a bar under it. A is a, with that symbol, is a member of B. If and only if all the elements of set A are also elements of set B. So then you can say set A is a subset of set B. Notice that bar means equal. That bar under here. See that? That shows equality. Okay. Now, if A is not a subset of B, then we symbolize it by that. We have again that kind of a prawn, but we go across it. Look at example 1, page 57. Example 1, okay, in the middle of the page. It says write whether it's a subset or not, between subset or not relationship between these sets. For example, number A, set A is 1, 3, 5, 7. Number B has members 1, 3, 5, 7, 9, and 11. Is it the question is, should we write it as is it a subset or is it not? Why?
Yeah, the set is 1, 3, 5, 7, 9, 11. So the element.
Yeah, but you see,
the subset would be the other numbers, but like they're repeated, they are in the same.
Okay.
The same set. But what about the 11? Yeah, that's why it's a subset.
Yeah, set A is a set A is a subset of set B because it all the elements of set A are also contained in set B. So we can write that down. We can say yes. But look at number B. A set, they put it in a roster form. X is a letter in the word proof, and Y Y is a letter, the other said, well, why, when Y is a letter in the word roof, are they, and it asks the question, is A subset of set B or not? Are all the members of set A, P, R, O, O, F, are in set B? No, so it's not. Or look at C. X is a planet of Earth solar system, and then B is Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. So is A subset of set B? Yeah, because all the elements of set A are also in set B. Okay. So if remember, it doesn't mean that all the elements of the two sets should be equal. If that's the case, the two sets would be equal. But it means that all the elements of the set A, the first set, must be in the second set.
So the order matters.
Yeah. Okay. Now, the order matters as far as when I say which one is first set and which one is the second set. But the members can be all over. It doesn't matter. Okay. Now, we have something else called proper subset. Set A is a subset if set A is a subset of set B, but not equal to. Then it's called a proper subset. For example, let me and note for proper subset we use that sign without a bar. For a subset we use the sign with a bar. Look at page 58. And review it. Okay, it says set A is a proper subset of set B, expressed as a proper subset when you have that sign without a bar. If set A is a subset of set B and set A and B are not equal. For example, use the example before below it. Set A has members 1 and 3. Set B is the members are 1, 3, and 5. Here we can say set A is a subset of B because every element in A is also is an element of B. But when you have it's the same two set 1 and 3 and 1 and 3 and 5. We can say A is a proper subset of B because A and B are not equal. You see, so two sets can be both, can have the relationship between them both as a subset and a proper subset. You follow me? Okay. Let me see further example. Or again 1, 3, 5. Of course, 1, 3, 5 is these are equal sets. If you look at page 59, it says set A X when X the person and X lives in San Francisco. Set B X is a person and X lives in California. Okay, so is it a subset or is it a proper subset? Yeah, actually, no, actually, look, set A is a proper subset of set B. What did you say? Okay, proper subset because they are not equal. So you can live in San Francisco and then you're in California, but doesn't, not all people live in San Francisco. Okay, so set B is much bigger than set A. Look at number B. You have set A 2468, number B 2846. Are they subset or a proper subset? Okay, if it's because the members, they have exactly the same members, so it's a subset. Yeah. It's not a proper subset, so we cannot use. We have to use that little bar. Okay, are you following me?
Yeah.
Okay, I hope you're not confused. Okay, so we looked at example 2, page 59 also. Okay, it says study tip, do not confuse a symbol. Okay, yeah, don't confuse that E sign with a member and a bar. The E sign means an element. If you look at the bottom of page 59, the E sign means it's an element of or a member of a set. The symbol that kind of a fallen U with a bar means is a subset. So don't confuse that. Like 4 is a member of the set 4 and 8. But if I put braces around 4, the first set is a subset of the second one. And it's not, you cannot say the symbol, you cannot use the symbol of membership, because we are talking about set 4, not just a number 4. Follow me? Yeah. Okay. So that's when there is that following you with a bar means it's a subset. When it's only that prong shape figure, it means it's a proper subset. Okay. Subset for every set A, the difference between subset and a proper subset, try to summarize it here. For every set A and B, set A is a subset of set B, where if every element in set A is also in set B. Now, set B, again, remember, can have more other members too, okay? Proper subset for set A and B, set A is a proper subset of set B if every element in set A is also in set B, but set A does not equal to set B. Okay. All right. Actually, when we use subset, actually the two sets are equal. So I take it back. When I said set B can have a larger members according to this definition and example that we have here. No, all right. Okay, I hope you're not confused. Okay, you're okay.
I think so.
All right. Now, empty set as a subset. The empty set, again, that null figure, the empty set is subset of every set, and it's symbolized by 0 and a bar going across it. Furthermore, empty set is a proper subset of every set except itself. Like for any set B can be any set. You can have an empty set is a proper subset of it. Okay. All right. For any set B other than empty set, also it's for any set B. If I don't specify other than empty set itself, null is a subset of of B, and for any set B other than the empty set, null can be proper subset of. Okay, you follow me? All right. Now, we have also something called complements of set A, which is symbolized by that kind of a blue color area, A prime. A prime is a complement of set A, and is a set of all the elements in the universal set. Universal set considers both of them together and put them, that would be universal set. You have A, that circle, and its complement is the surrounding area, A prime. You know, these things can be used in ministry for studying. For example, let's say you are doing church planting, you look at your neighborhood, the place that you're starting the church, the city, and you look at, you know, if you want to reach out, for example, to Hispanic or to the Muslims or some specific group, you can draw these diagrams and get information from city about the, you know, sometimes, I don't know, yeah, you can get information from the city, the names, you can, if you know Hispanic names, Middle Eastern or Muslim names, and you can identify and then draw a diagram and then use that as a focusing on a specific area. All right. Now we can have intersection between different sets. For example, intersection between set A and B is symbolized by that yellow area, A, and then you have that reversed inverted U. And then that white area, you have intersection between A, B, and C. Or between A and C is that purple area. And between B and C is that blue area. Okay, so intersection means, and you're looking at area that the members are both in set A and set B, for example, that yellow part. Okay. And union means it doesn't matter, it can be either in this one or other one. The union of set A and set B is symbolized by A, U, B. So the set contains all the elements that are members of set A or set B, both sets. So union of A, B, or it's same as union of B, A, as you can see in that picture. Okay. So I wanted to make sure that you are clear as far as the difference between subset and proper subset. Okay, remember, the proper subset is when set A, its member is part of set B, but they are not equal. Okay, that's called proper subset. You don't have that bar under that conch shape of figure. But if the members are part of it, has to be in order to be any kind of subset, and they are equal, then it's called just subset. A proper subset meaning they are not equal, okay? But the elements are set A are in set B, okay? Is that clear?
Yeah.
Now, we have something, it's called Venn diagram, and Venn diagram was widely used diagram, shows logical relationship between set and was popularized in the 19th century by John Venn. As you can see, for example, these three circles, A, B, and C, and set A, you can set A is A members of A plus D plus G and plus E. So you have, you know, that first circle, A, D, G, and E, okay? When I say set A, it has this part, that part, that part, that part. Set B has B, F, G, D. Set C has C, E, G, F. Okay, now this is a good, by the way, the videos that I put on Populi, please watch them. It can help you to in understanding the material. Let's watch this one together here. It's a good one.
Smooth, sweet, fruit, fruit, yellow, sour, pumpkin.
Okay. So, you can use this Venn diagram again in studying of your church, or even, let's say you are working with a young youth group at the Arabic church. You can use that Venn diagram to study what are common and what are not common among these students. So to focus on your lessons or focus your activities. Okay. All right. Okay, for example, again, if we have two set of soccer players, set of tennis players, you have Alex, Casey, and Drew, and Hunter, and Casey, and Drew, and Jade in the tennis. Then if you want to write a union, would be all the members, Alex, Casey, Hunter, Drew, and Jade, the union of these two sets. The intersection, meaning people who play both of them. The union means people who play either soccer or tennis. This one means the people who play both soccer and tennis. You only have Casey and Drew. All right. Now, if you say the difference of the two sets, you want to know the people, the difference between soccer, the ones who are playing soccer and the ones who are playing tennis, then you have only the people who only play soccer they are Alex and Hunter. All right. So in summary, U is union, is in either set. The inverted one is intersection, must be in both set, and then you have the minus sign is the difference in one set, but not in the other one. Let's say, for example, there's a third set, which is volleyball, which Drew, Glenn, and Jade play in it. So we have a set volleyball with Drew, Glenn, and Jade as its member. S is a soccer player, T for tennis player, and V for volleyball player. So you have the Venn diagram would be something like this. You have these three circles, soccer, tennis, and volleyball. For example, you look at Drew here. Drew plays all the three, soccer, tennis, and volleyball. Jade is here. He plays volleyball and tennis. Alex is here. He plays only soccer. And here, you see, this area is empty, so there is no one plays only tennis. All right. We have people who play only soccer, and but we don't have anybody who plays only tennis. Casey plays tennis and soccer. Drew plays all three. Jade plays tennis and volleyball. All right. Okay. Set S. This is just a set for the soccer player, so it's Alex, Hunter, Casey, and Drew. Union of set, for example, set T and V, so it means you have Casey, Drew, Jade, and Glenn. And see that you write it like this: T union V, and then you put the braces and write the members. Okay. Intersection of set S and V, the one that it's a member of both, plays both soccer and volleyball, is Drew, and this is the area. Okay, and you see, you write it like this: S intersection V. And what is that area there? That's an empty set. The intersection of, you have intersection of S and V minus T. There's nobody who plays only tennis. So it's an empty set. All right. And then the universal set would be if we have these guys here who are not playing any of these, but they're, I don't know, let's say part of a class. Blair, Erin, Francis, and Ira, when you want to write the universal set, you have to include them too. Okay. Everyone who does not play soccer, then, so notice the question. You want everyone who doesn't play soccer. It doesn't say that you must play something. So soccer player are these: Alex, Hunter, Casey, and Drew. So you take them off, you have Jade, Glenn, plus these guys. Okay. Complement everything that is not S, everybody that is not playing soccer. So these are the soccer player. So its complement or S prime would be Jade, Glenn, Blair, Erin, Francis, and Ira. Okay. And you write it as S prime. So let's look at page 68. Example 3. So you have, let U be, the natural number from 1 through 9, including 1 and 9, and set A is 1, 3, 4, and 7. Find A prime. Meaning, what is A prime? Everything not A. So you look at U and you cross those members that are in A. 1, 3, 4, 7. You cross them, so the set A primes is 2, 5, 6, 8, and 9. You follow?
Yeah.
Good. Why are set important? They allow us to treat collection of mathematical objects as mathematical objects. You will see everything we do in algebra, in mathematics, has to do with set. The starting point to any mathematics is the definition. And without set, we would be hard pressed to give definition of most mathematical objects. Definition relying upon set, one of them very, very important thing you see in mathematics, you see in algebra, are called functions. A function is a rule that maps numbers to other numbers. But also, again, rule kind of at this point, when we talk about rule, we are kind of vague. But for example, if I have 2x, meaning 2 times x, that's a rule, that's a mathematical operation. And I have 2x plus 1 minus 1. Now, there are different rules, but they are calculated in different way, but they yield the same output. So you can think of a function as a box. You put an input and comes an output. Now, it can have more than 2. You can put 1 and it can have, actually, no, you see, like this is one box, 2x, and that the other one is another box. Now, they can have the same result, but they are different functions. Okay. So we define a function as a set of ordered pairs. In chapter 6, we'll see the domain of the function. Function maps numbers to numbers, but the same concept of rule that maps things to things pops up all over mathematics. Then you have operators, map functions to numbers. Operation in group maps, abstract group elements to other elements. Don't be afraid about this. I think it will be make it much more clear as we go through example. And then we have strange function might map equivalent classes of infinite sequences to infinite set of rational number and so on. But you can't precisely pin down what things means unless you have a mathematical notation, and that's when we need set. Okay. Now this diagram shows exactly very well what is a function and what's a non-function. You see, as I mentioned, 2x and the other one, 2x plus 1 minus 1. Now, a function, you put the input, it can be like this. A give you x, B give you y, C give you z. Or, like that example, you can have 2 different boxes that give you the same number. That's okay. Or C give you z. That's still a function. But these are not functions. So if I have 2x, let's say, which one time points me, let's say, to 4 and another time points me to 6, that's not a function. There's a problem there. Can't be that. I can have, you can have 2x plus 1 minus 1. That's a function, even though these are different boxes, but they can point to the same number. That's okay. But you cannot have a same box, same rule, and with 2 different outputs. That's not a function, like here. Or, okay, even A points to Y, okay, that's good. But then you have B going to Y and Z, C going to C and Z. This is many to many. That's not a function. All right. Now, what is the function? Because understanding that will help you as when we go to algebra. So let's watch this video.
A function, and I'm going to speak about it in very abstract terms right now, is something that will take an input. It will take an input and it'll munch on that input. It'll look at that input. It'll do something to that input. And based on what that input is, it will produce a given output. So what is an example of a function? So I could have something like f of x, and x tends to be the variable most used for an input into the function, and the name of a function tends to be the most used variable, but we'll see that you can use others. But we could have f of x is equal to, let's say, x squared if x is even, and let's say it is equal to x plus 5 if x is odd. So what would happen if we input 2 into this function? And the way that we would denote inputting 2 is that we would want to evaluate f of 2. This is saying let's input 2 into our function f. And everywhere we see this x here, this variable, you can kind of use this as a placeholder. Let's replace it with our input. So let's see, if 2 is even, do 2 squared. If 2 is odd, do 2 plus 5. 2 is even, so we're going to do 2 squared. So in this case, f of 2 is going to be 2 squared, or 4. Now, what would f of 3 be? Well, once again, everywhere we see this variable, we'll replace it with our input. So f of 3. So 3 squared if 3 is even, 3 plus 5 if 3 is odd. Well, 3 is odd, so it's going to be 3 plus 5. It is going to be equal to 8. Now, you might say, okay, that's neat, Sal. This was kind of an interesting way to define a function, a way to kind of munch on these numbers. But, I could have done this with traditional equations in some way, especially if you allowed me to use the squirrely bracket thing. What can a function do that maybe my traditional toolkits might have not been as expressive about? Well, you could even do a function like this. You could have, and let me not use f and x anymore, just to show you that the notation is more general than that. So I could say h of a is equal to the next largest number that starts with the same letter as variable a. It says as variable a, and we're going to assume that we are dealing in English. So given that, what is h of 2 going to be? Well, 2 starts with a t. What's the next largest number that starts with a t? Well, it's going to be equal to 3. Now, what would h of, I don't know, let's think about this. What would h of 8 be equal to? Well, 8 starts with an e. The next largest number that starts with an e, so it's not 9, 10, it would be 11. And so now you see it's a very, very, very general tool. This function is this h function that we just defined. We'll look at it. We'll look at the letter that the number starts with in English, and so it's doing this really, 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 really wacky thing. Now, not all functions have to be this wacky. In fact, you have already been dealing with functions. You have seen things like you have seen things like y is equal to x plus 1. This can be viewed as a function. We could write this as y is a function of x, which is equal to x plus 1. If you give as an input, so let me write it this way. So for example, when x is 0, we could say f of 0 is equal to, well, you take 0, you add 1, it's equal to 1. F of 2 is equal to 2. You've already done this before. You've done things where you said, look, let me make a table of x and we take and put our y's there. When x is 0, y is 1. When x is 2, I'm sorry, this was when x is, a little mistake, where f of 2 is equal to 3. And you've done this before with tables where you say, look, x and y, when x is 0, y is 1. When x is 2, y is 3. So this, you might say, well, what was the whole point of using the function notation here to say f of x is equal to x plus 1? And the whole point is to think in these more general terms. For something like this, you didn't really have to introduce function notations, but it doesn't hurt to introduce function notations because it makes it very clear that a function takes an input, takes my x, and this definition, it munches on it. It says, okay, x plus 1, and then it produces one more than it. So here, whatever the input is, the output is one more than that original function. Now I know what you're asking. All right, well, what is not a function then? Well, remember, we said a function is something that takes an input and produces only one possible output for that given input. So for example, something like, and let me look at a visual way of thinking about a function this time, or a relationship, I should say. So let's say that's our y-axis, and this right over here is our x-axis. And let me draw a circle here that has radius. Let me draw a circle here that has radius 2. So it's a circle of radius 2. This is -2. This is +2. This is -2. So my circle, it's centered at the origin. It has radius 2. So that's my best attempt at drawing the circle. Fill it in. So this is a circle. The equation of a circle, of this circle, is going to be x squared plus y squared is equal to the radius squared, is equal to 2 squared, or it's equal to 4. So the question is this relationship between x and y, here I've expressed it as equation, here I've visually drawn all of the x's and y's that satisfy this equation, is this relationship between x and y a function? And we can see visually that it's not going to be a function. You pick a given x, let's say x is equal to 1, let's say x is equal to 1, there's two possible y's that are associated with it. This y up here and this y down here. We could even solve for that by looking at the equation. When x is equal to 1, we get 1 squared plus y squared is equal to 4. 1 plus y is equal to y squared is equal to 4. Or, subtracting 1 from both sides, y squared is equal to 3. Or y is equal to the positive or the negative square root of 3. This right over here is the positive square root of 3, and this right over here is the negative square root of 3. So this situation, this relationship, where I inputted a 1 into my little box here, and associated with the 1, I associate both a positive square root of 3 and a negative square root of 3. This is not a function. I cannot, when associated with my input, two different outputs. I can only have one output for a given input.
Oh, so, it wasn't enough. Okay, let's see, yeah, it's working. But in that last example, remember, even though that is not a function, but it still is a valid equation. Okay. All right. Let's move on. So algebra, we need these sets and these terminology because algebraic structures or topological spaces are more considered as a set with operation under them. Notice in the when he was talking about function, you have you have some kind of rule, an operation that is done on a number. In order to be a function, one output, the function must always, when one input must always give one output. But remember, like in that last example, you can have an equation can be not a function, but a valid equation. Okay, all right. Now we come to kind of fun part: numbers, representation, and calculation. Let's see, it's yeah, we can go. We still have 10 minutes. Different numerical system: Hindu, Arabic, Egyptian, all that, Babylonian, Mayans. The thing about number system is system of numbers consists of a set of basic numerals and rules combining them to represent number. We can have place value or positional value number system. The value of symbol depends on its position in the representation of the number. For example, look at number 20. The 2 in 20 represent 2 tens. And the 2 in 200, same 2, but we change its position, represent 2 hundreds. Okay, so our number system is a positional value number system. By changing that digit to different position, you can have different numbers. A true positional value system requires a base and a set of symbols, including symbols 0 and 1 for counting number less than the base. And the most common positional system is a base 10, which we use, system which is called decimal number system. Now you have Hindu Arabic numeration system. Hindu Arabic numeration system requires fewer symbols, and that's why it became universal, and other numeral system did not survive, because it became impossible to do operation within Babylonian or Roman or Mayan. They don't have zero, and in a Arabic Hindu with these 10 digits 0 through 9, we can do all the numeration that we want. Number 1 through 12, these are simple things. They have their own names. Number 13 through 19 have tens as an ending, and then the ending is blended with the names for numbers 4 through 9. Numbers from 20 to 99, tens places is named for first, followed by a number from 1 through 10. Numbers from 100 to 999 are combination of 100 and previous names. And these are very simple things. Each Hindu Arabic numeral has a word name. So, you have, those are obvious one. For this one is 56,000, because this is in a position of 1,000. Okay. That is like this one is 570, position of the 100 and then the 7. Now we have exponential notation, which means b to power of n. If n is a natural number, bn means b times n times. Okay. Is that the nth power of b, or b to power of n. And this expression, this kind of writing is exponential expression. And remember, any number to power of 1 is equal to itself. Any number to power of 0 is what? 1. Remember. So let's look at example on page 195. Example 1, top of the page 195, you have evaluate the following, like A is 10 to power of 2, means 10 times itself 2 times. So you get 100. 10 to power of 3 means 3 times 10, 3 times multiplied by itself, you get 1,000. 10 to power of 4 is 10,000. 2 to power of 6, meaning multiply 2 by itself 6 times, you get 64. 1 to power of 7, 1 to power of any number is always equal to 1, and any number to power of 1 is equal to itself. So 7 to power of 1 is 1. Okay. All right. So far, don't be intimidated by these lessons. I know they can be a little bit confusing, but don't be intimidated. Okay. Positional value. The positional value in the Hebrew, Hindu, Arabic system are like this, starting from this side, the right-hand side, 1, 10, 10 to power of 2, 10 to power of 3, 10 to power of 4, 10 to power of 5. So we always multiply the first digit on the right by 1, the second digit by 10, the third digit by 100, the fourth digit by 1,000. For example, if you want to expand, you have 570, okay? If you want to write in an expanded notation, start from 2, multiplied by 1, okay? Start then 7 multiplied by 10. 5 multiplied by 10 to power of 2 or 100, then add them together. But when you write it like that, 500 plus 70 plus 2, that's an expanded notation. All right? Numerals in expanded form, just what I just said. So in general, we multiply the digit n places from the right by 10 to power 10 to power 10 to minus 1. I know this can be confusing, but the example makes it clear. Let's say we have this number, 1,234. We want to write in an expanded notation. So this is what you do. Just write 1, 2, 3, 4, 1,234 equal to. Then take each digit, separate them. I take 4, 3, 2, and 1. Start from here. It's 10 to power of 0. Makes it what? 1. This is the first position. First 10 to power n is 1. 1 minus 1 is 0. 10 to power of 0 is 1. Follow me? The second one, second position, n is 2. So it's 2 minus 1. 10 to power of 1 is 1. So 3 times 10. Okay. So we are in a third position. So it's 10 to power of 2. We are in the fourth position. It's 10 to power of 3. If we were, let's say, in the 8th position, it would be 10 to power of 7. All right. So then you can either write it like this or write it. This would be an expanded form. If in a quiz or a test asks you, that's what I want. We have Babylonian numeration system. And again, these systems failed because they didn't have 0. It's the oldest known numeration system, but again, because of the problem of lack of 0, these systems fail. The Babylonian system is a place value system with a base of 60, or sexagesimal system. Base 60, basically. It's not a true place value system because it doesn't have a symbol for 0. That causes lots of confusion and ambiguity. The positional value in the Babylonian system are like this. the first one would be 1, second digit 60, then 60 to power of 2, 60 to power of 3. Let's, for example, look at page 197. And you need to have that table 4.1 because we don't, we are not Babylonian, we don't have these things memorized. So, for example, look at that middle of the page, even before the example. It gives you, you know, that symbol like a, here, you know, these. It wants you to find this number. And then symbol like this, and a symbol like this. Yeah, okay. Now, we look at that table, V is 1, and the other symbol is 10. So this is 1, this is 10. Don't worry about the positional place right now, just we want to write the digits, the value. And this one is 2 of this size, which would be 1 plus 1. Okay? So, another color. I got this from that table. Okay. Now, we again we need to know this from the given from the problem itself about the positional value of the Babylonian numeration system. This first one again is that what was the base? Remember? Yeah, base is 60. Okay, so I put 60 for multiplied by 60, multiplied by 60, multiplied by 60. Okay. Now the first one, this is the first position. Remember the rule, n minus 1. 1 minus 1 is 0, so that makes it 1. Okay. All right. This is position number 2, so it's to power of 1. This is position number 3, it's to power of 2. So we get 4. We get here 1 times 60 times 6 is 3600 plus 10 here times 60 plus 1 plus 1 is 2 times 1. Okay, so you do all of that, you get 3600 plus 600 plus 2, and you add them up, so you get 4202. Yeah. So this number in a Babylonian system is equivalent to this number in our system. Okay. All right. Also says look at page 198. Oh, okay, that's the Mayan system. Well, okay, well, there's that. There are other examples similar to this there, but the Mayan numeral. But let me get to that first. This is again a table that is right there on page 198, table 4.2, the Mayan numeral, and I have it there for you also. It's kind of tricky because it goes vertically. And these are from the clays from Maya. Okay, here, let's look at this example. And I simplified the numbers just for the sake of easier calculation. If you have this number on the A column, all right, I look at table 4.2 and I start from the bottom one. You have, let's see. Okay, 1 bar, if you look at the table 4.2, 1 bar is equal to what? Look at table 4.2. 5. When you have 2 bars is equal to what? 10. So 10, and again, you need to have this positional value. We are not Mayan. We don't have these memorized. The positional value for and that's the first number. That's the first position. Again, it's 2 power of 20 to power of 0, which is 1. So that's why you get 10 times 1. Or let's first figure out the value numbers, then we figure out their positional value. So the first 2 is 10. That's oval shaped thing. What is that? Yeah, from the table. When you have only 1 dot, 1. When we have 2 bars and 2 dots, 12. Because 5 plus 5, 10, and plus 2 1s, 12. Okay, so that's where we get those 12, 1, 0, and 10. Okay, now about their position, let's start from the beginning. The first one is 20 to power of 0 is 1. The second position is 20 to power of 2 minus 1 is 20. Then the third one is 20 to power of let's see, 20 to power of it's a third position, 3 minus 2, 2. So 20 times 2, 400. Okay. And then we get to the fourth position. So it's 20 to power of 3, but I made it easier. I made it simpler. So we will not get confused. So it would be 20 to power of 3. I just made it 8,000. Okay, so 400. So 20 times 20 times 20 becomes 20 times 20, 400. 400 times 20, 8,000. You follow me? Okay. So then we multiply these are the positional value by those numerical value. We get the column C. Okay. Okay, 96,400, 0 plus 10. We add them up, we get 96,410. Did you guys follow what we did here? Okay, if you look at the textbook, look at example number 5 at the bottom of page 198, example 5, using Mayan numerical system and number A. Okay, remember, start from the bottom and go up. So you have 2 bar and 2 0. First, let's find the value. What is 2 bars? 2 bars, the value of 2 bars, each bar is 5. So 10, 5 plus 5, 10 plus 2 dots becomes 12. Okay, so that's the Hindu for Arabic numeral. The second one is 1 bar plus 2 dots, 7. Third one is just that owl shape thing, 0. And the fourth one, 2 bars plus 4 dots. So we got the second column. Okay, we got that using that table. And in the quiz or test, it will be given to you. I'm not expecting you to memorize these things. Then we'll go to the place value. So the first one, now we are in third column. It's to power of, it would be n minus 1 to power of 0, which is 1, okay? The second one, it's 20 to power of 2 minus 1 is 20, okay? Third one, now here the thing changes. The thing changes. That's the thing that creates mistake and confusion, and you need to have these information in the textbook. The third position, it's not that easy. You know, I rounded up in my example to make things easier for you. You see, I didn't use 18. I just keep using 20 to make it easier. But it's actually 18 times 20 times 0, which makes it 0. The fourth one is 20 times to power of 20 to power of let's see, 4. Actually, you see what he did, he separates 18. What I did, I just called it 20, another 20 to make it easier. Okay, so then you find the place value, you do the multiplication and you add them together, you get the value 100,952. You follow? So notice what I did, I simplified the numbers. Instead of using 18, I just made it 20. Okay. This I couldn't put this. This is a, you know, it's on the Populi. I encourage you to take a look at it. You can, if you go to that page, it gives you an interesting example. You know, it's right there in the Populi. Just copy and then put it on your, you know, Google or whatever, and go there, and it shows you interesting example of doing calculation, simple addition in Mayan numerical system. Okay. So, example, no, we did that already. Yeah. So, now, Greek numeration system, you have, you know, you have the numbers from 1 to 900 with their names and their symbol, alpha, beta, gamma, all of them. Then you have this Roman numeration system, and believe me, the problem, you know, when in any culture, when they don't come with the number 0 and simple base and positional operation, that civilization is doomed to fail. Because, you know, just imagine if you are an engineer using Roman numeration system. I mean, it would be impossible. You know, but it would be impossible to create calculators, computers, and all that. But for example, I put 154 is equivalent to CLIV numeral system. And if you go there, you can check it and see it, right. 1,492 same equal to, look at it. What, I mean, God, it becomes so big, just adding 1 digit. Huge. Or another example, you know, look, I mean, incredible. Even the same problem with the Hebrew numeration system. But Hebrew numbers don't have a base because they are not a positional numeral system any more than Roman, same problem. The number 764 in Hebrew would be written from right to left as that. Okay. The value is calculated as 4 plus 60 plus 300 plus 400, 764. All right. Okay. Now, number bases in positional system. Any counting number greater than 1 may be used as a base for a positional value numeration system. So you have in general, let's say base as a B. So it's the position, the very first one is n to minus 1, which makes it 0. So you have you get always 1. Okay. Then second position 2 minus 1, and it keeps going on. You just 1 less than the position. The third position is b to power of 2, b to power of the fourth position is to power of 3. So if the base is if the number system base is 8, that's what you get. 1, 8, 8 to power of 2, 8 to power of 3. And if the number system base is 2, that's what you get. Computers use binary system 0 and 1 base 2, and octal system base 8, and sometimes hexadecimal system in computer languages. Now, for example, if we want to convert from base 6 to base 10, let's say we have a number 453 base 6. We want to convert it to our numerical system. So the way to, again, write 453 base 6 equal to, then separate the digits 4, 5, and 3. Put them in a parenthesis with additional addition sign in between. The first position is, again, remember, we are, this is base 6. So it's, but it's a first position, so it's n minus 1, 1 minus 1, 0. So you get 1. So it's 3 times 1. Okay. The second position is 2 minus 1. So you get 6 to power of 1, you get 6. The third position is 6 to power of 2, 1 less than the position, and you get 6 to power of 2, 36. So you do the multiplication and addition, you end up with 177. So in a base 6, 453 is equivalent to 177 in base 10, our base. Notice the difference. You know, it's smaller. It's almost 1/3. That means you can do much more multiplication and investigation, multiplication, study with base 2 in comparison to base 6. Because if you're using base 6, the numbers become huge. You know, it's almost 3 times what we have from almost 177 to 453. Right? Let's say if you want to convert from base 8 to base 10, again, the same method. You know, we have a number 3,615, but base 8. We want to know what that would be in our base system, base 10. So just separate those digits 3, 6, 1, and 5, as you can see there. So you have 3, 6, 1, and 5. Put parentheses, plus sign, parentheses, plus sign. It's base 8. Okay, again, remember the first position is 1 minus 1, 0, so that becomes 1. This is to power of 1, power of 2, power of 3. So we have base 8 to power of 3, 8 to power of 2, 8 to power right? That's a base system, okay? So you do you raise these numbers to the exponent, you get 5, 12, 64, 8, and 1, and then you multiply, add them, you get 1933. And again, notice from 3615 to 1933. You know, this is just on the side. I'm saying one of the reasons that the other numerical system couldn't work, beside the fact that they didn't have zero, and even if a system does have zero, if the base is other than 10, the problem would become the numbers. When you do a multiplication, the numbers become huge. All right. Converting from base 2 to base 10, and again, this is another one. We are given this number, 101101, base 2. Separate the digits, 101101, okay? Then base is 2, so we put 2, 2, 2, 2, 2, and order. This one is to power of 0 becomes 1. This is 2 to power of 1, 2 to power of 2, 2 to power of 3. So you see, the fourth position is the power becomes the position minus 1. Okay, the fifth position and the sixth position. And you do the multiplication, you raise the numbers to the exponent and do the multiplication, you get 45. Look at it. You know, that huge number is 45 in our numerical system. Okay. I think we can finish right after this. Let's look at page 204, example 3. Convert EC7 base 16 to base 10. So, and we need that table right on the right side. Otherwise, we don't know what we are talking about. So you write the digit EC7, 7 is 7, C is 12, E is 14, then the base is 16. So you write the base, and remember the first one always becomes 0. 16 to power of 1 for the second position, and 16 to power of 2 for the third position. And again, you do the multiplication, you get 3,783. I'm not going to ask you to do division to convert from base 10 to base 8. No, that really becomes too confusing. So you don't need to look at that. Okay. Review example 208 to 11. Okay. Okay, so it has look at example 1 on page 208, adding 33 base 4 plus 14 base 4. Now, what you have to do is to convert each of them to base 10. When you follow the same procedure, is 33 is 3, again, separate the two digits, times base 4, 3 times 4, and 3 times 4 to power of 0. It ends up with 15, and you do that for the second number. Again, separate the digit, put the base, and do the exponent. You multiply, you add them together, and you get 22. That would be number, the value is in our numerical system. Okay, which you see that at the bottom. It says 15 plus 7 is 22. Our work is correct. But the way he did that here, he also added 3 base 4. 3 base 4 is equal to 6 base 10, we are not dealing, equal to 6 base 10 is equal to, okay, 1 times 4 plus 2 plus 1, 12 base 4, and then now we record the sum of the right-hand column, 12 plus 4, 12 base 4. We place the digit on the left above the 4 columns. So you add them up together in base 4, and you got 2, and for the second one, you get 5, and then you add them together, so you get 112, 4. Don't be confused about them. I'm not going to ask you to do calculation in other base number. I may ask you to convert them to base 10 and do the addition. Okay? Are you guys okay?
Yeah.
Okay. All right. Well, that's it. Any question?
Yes, I have a question regarding the syllabus.
Okay, go ahead.
I was like confused. Because I know that I have the column of to do thing. For instance, the reading report of Nico.
Mhm.
But I don't know about this book. This book shall we also go through it, the chapters you
Oh, just study them, look at, you can follow with I tried my best that the PowerPoint be clear. But I encourage you to go through the lessons. You don't have to, but let's say when there's something, let's say like these different base numerical system. If you go to those chapters, I think you see a lot more examples, but there's nothing for you to report except these help you for your quizzes, for your assignments.
just like for consultation then.
Yeah, for presentation.
Consultation.
Oh, consultation, yeah.
Yeah.
Yeah, okay, yeah.
Yeah, for the presentation.
Yeah. No.
All right.
Any other question? Everything, it was the lesson clear for you. If there's anything
Yeah,
ambiguous,
okay.
don't be too worried about these additions and division in other number system. I'm not going to ask you that. Okay. All right. So if no other question, let's end our time with a prayer. Can I ask you, brother, to pray for us?
Heavenly Father, we thank you for this day, Lord, you have given us. We thank you for the opportunity to learn about math and how this discipline shows your glory, shows your world, and we can understand it better and glorify you. Thank you, Lord, for all the blessings that you have given us, Lord, and thank you that you're so good. And Lord, we pray that you continue to bless us, Lord, to give us diligence as we work through the assignments, Lord. And yeah, we pray this in the name of your Son, Jesus. Amen.
Amen. Amen. All right, thank you. And let's finish this.
Thank you.